Computability theory, also called recursion theory, is a branch of mathematical logic, of computer science, and of the theory of computation that originated in the 1930s with the study of computable functions and Turing degrees. The basic questions addressed by recursion theory are, what does it mean for a function on the natural numbers to be computable, and how can noncomputable functions be classified into a hierarchy based on their level of noncomputability? The answers to these questions have led to a rich theory that is still being actively researched. The field has since grown to include the study of generalized computability and definability. Invention of the central combinatorial object of recursion theory, namely the universal Turing machine, predates and predetermines the invention of modern computers. Historically, the study of algorithmically undecidable sets and functions was motivated by various problems in mathematics that turned out to be undecidable. For example, word problem for groups and the like. There are several applications of the theory to other branches of mathematics that do not necessarily concentrate on undecidability. The early applications include the celebrated Higmann's embedding theorem that provides a link between recursion theory and group theory. Results of Michael O. Rabin and Anatoly Maltsev on algorithmic presentations of algebras, and the negative solution to Hilbert's 10th problem. The more recent applications include algorithmic randomness. Results of Saur et al., who applied recursion theoretic methods to solve a problem in algebraic geometry, and the very recent work of Slayman et al. On normal numbers that solves a problem in analytic number theory. Recursion theory overlaps with proof theory, effective descriptive set theory, model theory, and abstract algebra. Arguably, computational complexity theory is a child of recursion theory. Both theories share the same technical tool, namely the Turing machine. Recursion theorists in mathematical logic often study the theory of relative computability, reducibility notions and degree structures described in this article. This contrasts with the theory of sub-recursive hierarchies, formal methods and formal languages that is common in the study of computability theory and computer science. There is a considerable overlap in knowledge and methods between these two research communities. However, no firm line can be drawn between them. For instance, parametrized complexity was invented by a complexity theorist Michael Fellows and a recursion theorist Rod Downey. Computable and uncomputable sets. Recursion theory originated in the 1930s, with work of Kurt Gödel, Alonzo Church, Alan Turing, Stephen Kleene and Emil Post. The fundamental results the researchers obtained established Turing computability as the correct formalization of the informal idea of effective calculation. These results led Stephen Kleene to coin the two names, Church's thesis and Turing's thesis. Nowadays these are often considered as a single hypothesis, the Church-Turing thesis, which states that any function that is computable by an algorithm is a computable function. Although initially skeptical, by 1946 Gödel argued in favor of this thesis. Tashi has stressed in his lecture the great importance of the concept of general recursiveness. It seems to me that this importance is largely due to the fact that with this concept one has for the first time succeeded in giving an absolute notion to an interesting epistemological notion, i.e., one not depending on the formalism chosen, **. With the definition of effective calculation came the first proofs that there are problems in mathematics that cannot be effectively decided. Church and Turing, inspired by techniques used by Gödel to prove his incompleteness theorems, independently demonstrated that the Entscheidungs problem is not effectively decidable. This result showed that there is no algorithmic procedure that can correctly decide whether arbitrary mathematical propositions are true or false. Many problems in mathematics have been shown to be undecidable after these initial examples were established. In 1947, Markov and Post published independent papers showing that the word problem for semigroups cannot be effectively decided. Extending this result, Pyotr Novikov and William Boone showed independently in the 1950s that the word problem for groups is not effectively solvable. There is no effective procedure that, given the word in a finitely presented group, will decide whether the element represented by the word is the identity element of the group. In 1970, Yuri Matiasevich proved Matiasevich's theorem, which implies that Hilbert's 10th problem has no effective solution. This problem asked whether there is an effective procedure to decide whether a Diophantine equation over the integers has a solution in the integers. The list of undecidable problems gives additional examples of problems with no computable solution. The study of which mathematical constructions can be effectively performed is sometimes called recursive mathematics. The Handbook of Recursive Mathematics covers many of the known results in this field. Turing computability. The main form of computability studied in recursion theory was introduced by Turing. A set of natural numbers is said to be a computable set if there is a Turing machine that, given a number n, halts with output 1 if n is in the set and halts with output 0 if n is not in the set. A function f from the natural numbers to themselves is a recursive or computable function if there is a Turing machine that, on input n, halts and returns output f. The use of Turing machines here is not necessary. There are many other models of computation that have the same computing power as Turing machines. For example, the mu recursive functions obtained from primitive recursion and the mu operator. The terminology for recursive functions and sets is not completely standardized. The definition in terms of mu recursive functions as well as a different definition of recursive functions by Gödel led to the traditional name, recursive for sets and functions computable by a Turing machine. The word decidable stems from the German word Entscheidungsproblem, which was used in the original papers of Turing and others. In contemporary use, the term computable function has various definitions. According to Cutland, it is a partial recursive function, while according to Saw it is a total recursive function. This article follows the second of these conventions. Saw gives additional comments about the terminology. Not every set of natural numbers is computable. The halting problem, which is the set of Turing machines that halt on input 0, is a well-known example of a non-computable set. The existence of many non-computable sets follows from the facts that there are only countably many Turing machines, and thus only countably many computable sets, but there are uncountably many sets of natural numbers. Although the halting problem is not computable, it is possible to simulate program execution and produce an infinite list of the programs that do halt. Thus, the halting problem is an example of a recursively enumerable set, which is a set that can be enumerated by a Turing machine. Equivalently, a set is recursively enumerable if and only if it is the range of some computable function. The recursively enumerable sets, although not decidable in general, have been studied in detail in recursion theory.